edition of the Utah Forge Modeling and Simulation Community Meeting. A couple things we want to go over today. I'll provide a brief little input or update, and then I'm going to hand it off to two speakers today. So if my system will allow me, I'll give a brief update for the field schedule, and some of the other brief updates. The two things I'll talk about are the fracture plane fitting of the MEQ data and some flowback water compositional analyses that we just got back. So from the field access, things are just moving along, planning for the drilling of 16B. Also in conjunction with that, planning for flow testing, for reservoir testing, and all those associated activities. Still, to my knowledge, we're looking. The drilling will likely commence around the 1st of April. Is still the plan. Of course, that always is somewhat variability in there as we get closer. But I know John and Joe are working to start letting contracts, getting bids for all the different pieces and parts. So that is essentially still on track. No change from that from last month. And I know some of you have reached out to me regarding flow testing and reservoir testing and associated with that. We will be reaching out, having some more meetings, and we're still doing some work to try to better inform what some of those things can be. From internally, from the Forge team ourselves, we are actively working right now on providing some recommendations for the offset between 16A and 16B. That's in process. Likely, I know we'll have some presentations on that at AGU next month and also at Stanford. So perhaps we could get together as a community in Stanford. I'll leave that up for maybe next meeting. We could talk about that as a group, even maybe just formally get out to dinner or something over lunch. But anyway, I'm going to move on. The other thing, following up from last month, well, Alita presented her analyses and picks for discrete fractures from the MEQ data from the April stimulation. So those data have been uploaded into the GDR. They're there. They are still not available for download, and I apologize. It's awaiting curation. And I think that curation happens from our colleagues who run the GDR or OpenEI. I'll check to see when we can expect to have that, but I would expect in the coming days, those data will be available for download. If you're looking for the data and you don't seem to be able to get it in a reasonable amount of time, reach out to me directly and I'll apply some pressure or influence to the degree that I can to make that happen. The other hot off the presses, hot from the laboratory, is something I just wanted to put a teaser out here. So we did get some of the chemical analysis back from the sample analyses back from the flowback waters from the April stimulation. So I'm not going to get into any details or analysis or even just I'm going to provide some general commentary. Stuart Simmons, our head geochemist, presented this stuff to the management team just on Tuesday or Monday. And so a lot more work to be done here, but there's some very interesting things to see. So what you're looking at on all these plots are time of flowback increasing to the right and concentration increasing upward in all these plots. So I only showed 4 plots here: chloride, sodium, magnesium, and calcium. The key takeaway here, it looks like we're seeing some pretty interesting behavior. Of course, the longer we go in time here, the longer that water has had to be in contact with the reservoir. So essentially, you think contact time also increases to the right. Very interesting to see very large changes in chloride going down from in the 50 ppm or milligram per kilogram level up into nearly 5,000 for stimulation 1. So we may see a little bit more reactivity in some of these freshly fractured granitic rocks than we perhaps anticipated. A lot more work to be done here. Lots of uncertainty. I will be reaching out to some of our solicitation 1 awardees that are doing some geochemical or whole rock chemical analysis to try to leverage into them and see if we get anything to help control perhaps some kinetic rates for reaction. Try to understand these better before we really start doing deep dives into full geochemical transport and modeling. So that is coming. We may next month have a speaker. I might see if Stuart can present on these in detail for the next month's forum, but we'll go from we'll evaluate that as we go. That's the end of my slides. We do have 2 speakers today. I already mentioned Mukul Sharma from UT and Ahmad Ghasmi from OU will both talk about some of their recent stimulation modeling results. But before we transition away and let them speak, I will actually, if there's any questions for me now before I hand it off to them, please ask. I think we may get short on time. I know these two presentations we're going to see will be very interesting. And I'm sure there'll be lots of discussion. So if there's a question for me, you can please ask it now. As the other speakers come through, if you have a question, please type it into the chat and I will moderate those and kind of feed them off so we don't interrupt our speaker. Silence is golden. You guys hear me speak enough. Mukul, if you'd like to share your screen, you can take over and I'll stop sharing mine.
Okay, well, thank you. Let me see how this will work. You should be seeing my screen now.
Got it.
Okay. Well, I just want to thank everyone for attending and Rob for organizing this. The work that I'm going to present is work that has been done by one of my PhD students, Meng Cao, and Meng is on the Zoom meeting here. So Meng, you want to say hello?
Yeah. Hello, everyone.
So Meng is here. Any hard questions, go to Meng. But he will be, he's the person who's run these simulations and so forth. So the outline, looking at natural fracture characterization, which a lot of work that's been done by the Forge team, fracture propagation in well 16A. I'll talk about stage 1, just in the interest of time, history matching of net pressure, induced microseismicity, and then what are the different parameters that affect the geometry of the created fracture network. I'll also talk about some backbone, dead end, and isolated fractures and some future plans. So we essentially made sure that our wellbore trajectory and the observed microseismic events were consistent with what earlier folks had done. Fenella had done some work on looking at the geometry of the microseismic events and locating them, making sure that everything was consistent, which it is. So this is our wellbore and microseismic locations, and this is Fenella's, and they are consistent. The wellbore itself is oriented at 105 degrees north, 105 east, and that is at a slight angle to the direction of sigma h min. So you can see the orientation of these, and this is taken from the work done earlier again by other groups in the Forge team. So just to get you all oriented, the formation properties that we used and the geology also taken from some of the earlier work that is done by the Forge team, published in 2021. You all know this already, but the EGS part that we're simulating is down here in the 16A well. So I'll talk very briefly about the workflow for building our DFN. What we have essentially is data that has been analyzed by the Forge team earlier in terms of any log and core data. FMI data was the primary source, I believe, for a lot of the descriptions that they have. And what we do is to generate a DFN based on, in 3D, I'm showing you a 2D image, but it's a 3D description of the DFN. Where we want to make sure that whatever we generate is consistent with the observations from the logs and the cores. So here's the workflow that we have used. We basically look at the orientation of 4 sets of fractures that were identified by the Forge team. And these 4 sets have certain, I'll show you that on the next slide. Then there is also a length distribution. And an areal density that has to be determined. So we generate our DFN stochastically, and then calculate the number of fractures intersected by the cores in each set. So we have an artificial coring procedure that we do just like this, and see how many fractures we intersect and at what orientation. Compare these with the simulated intersections with the actual data. If they match, then that's the DFN we use. If not, we vary the areal density and make sure that we get a good match with this. So the 4 sets of fractures that were identified by the Forge team are shown here with these percentages. The length distribution with the minimum and a maximum is shown here with an exponent of 1.8. We have in our simulation geometry, we have 7,000 fractures. And so we have used this particular set of parameters for our geometry. The region that we're simulating is 200 meters by 400 meters by 125 meters thick. And this shows you, gives you an idea of what this DFN looks like in 3D. So it's a 3D rendition of all these all these 7,000 fractures with the 16A well placed in it. So just for scale, this is 50 meters. The model that we use to propagate the fractures is, we call it Multifrac 3D, which is the model that we have built over the last many years. It really consists of a reservoir domain, which is a compositional reservoir simulator. So it has reservoir pressure equations, component balance equations. It has a solid deformation equation, the displacement equation, which is essentially couples the poroelasticity. We also have a temperature equation for the reservoir. And so we have thermoelasticity in here. We have convection, thermal conduction, phase behavior coupled in the reservoir domain. We have the same in the fracture domain, where we have the temperature equation, the prop and volume balance equations, the fracture pressure equation, and the component balance equations. And of course, these are coupled together through leak off and through production, the fracture domain and the reservoir domain. We also have proppant closure and equations relating to how things between the fracture width and the proppant volume are related. There's a thermal flux coupling between the fracture and the reservoir. And then we also have the wellbore domain, where we have the slurry distribution and leak off into individual perforation clusters. And this is something that we've spent a good bit of time on. So we have proppant distribution, which then relates to the proppant volume equations going into each of the clusters that you create. There's wellbore phase behavior as well. So you can have phase behavior in the wellbore and a temperature equation as well. So it's a fairly complete model with all three domains being solved as completely as possible. With natural fractures, the primary differences that we have are in the fracture domain, where as the DFN is incorporated, we solve the displacement equations and the flow equations in the connected hydraulic and natural fractures. And of course, interactions between hydraulic and natural fractures are included. So the simulation options are, you can actually run it with different options. You can run it in 2D or 3D with photoelasticity on or off, multi-phase, compositional, or geothermal reservoir flow. I'll show you the formulation for the geothermal part here in a minute. The geomechanics options are, it has thermal poroelastic models, LEFM or DDM, displacement discontinuity methods, and thermal options, which are convection, conduction, thermoelasticity, etc. So all of these are included in this. I will say that what makes it possible, the model does become more and more complicated and slower as you add more and more features to it. So we want to be sure that we add only the relevant parts to it. The fracturing model itself is essentially solving the displacement problem with the pressure and the temperature coupled. The DDM part solves it at the fracture interfaces. If anybody has more questions and details, I'll be more than happy to walk you through some of this stuff. The interaction between hydraulic and natural fractures determines where the fracture propagates from the wellbore. So if you have multiple clusters, how exactly it propagates depends on the interaction between these, whether it crosses or whether it's captured by the natural fracture. And that's controlled by, we have different conditions. The simplest one that we're using here is Renshaw and Pollard. We have more complex fracture deflection conditions if you have strong poroelastic behavior where the matrix is porous, then this condition gets modified. The geothermal model is a formulation, is one that is an enthalpy formulation, which actually makes it very convenient to use steam tables and things like that, as opposed to a temperature pressure type formulation. This is an enthalpy formulation, and we essentially estimate the the phase behavior, the steam water phase behavior from the steam tables based on that. So this is something that's that we have done, and we have actually presented this and published this in the past. The parameters used in the model are shown here. Without going into them in any detail, there's the one thing I will point you to is this contrast in the horizontal stresses. The minimum horizontal stress and the maximum horizontal stress are different by about 800 psi, which is substantial. And as you'll see, this leads to more planar fractures than you would because of the high horizontal stress contrast, and the vertical stress is significantly higher. So those values were taken from some of the earlier work done by the Utah Forge team as well. I'll show you a couple of movies on showing you how the fracture. So this is stage 1 of the 16A well fracture propagation, and you will see the fracture propagates in length and in height. It is growing in both directions. You will see that the fracture growing in this direction is primarily planar. So because of the large stress contrast, you don't see a whole lot of turning occurring in this direction. And on the other side, you will see the turning begin to happen towards the later part of the pumping. And this turning on this side is a result of the large pressure drops that have occurred on this side, and that will cause some degree of turning happening on the other side. You will notice that the height of the fractures is constrained by the model so far, but we can certainly make the model bigger and try to see what happens as the fracture propagates vertically up and down. It's not geologically constrained, it's actually constrained by the parameters that we put into the model. If you try to visualize this in 3D, you can see, this is now turning the fracture as it's growing. You can see that it's primarily planar to begin with, but then later on, as you go towards this side of the fracture, you begin to see that the natural fractures are causing the fracture to turn as a result of the interaction of the hydraulic fracture with the natural fractures, and that turning behavior is observed late in the late stages of the pumping schedule. So this actually simulates the pumping schedule and creates this fracture geometry. The first thing we did when we modeled this was to try to do a history match of the net pressure between the simulations and what was observed in the field. So the blue lines are the data from the field. The red is the net pressure from the simulations, and of course you have the rate and so forth shown here as well. You get a decent match. It's by no means a perfect match, as you can see here. There's lots of funny things going on here, which I suspect are more related to initiation and some other things going on. But you do see a reasonable match of the net pressure over time. The formation of these fracture networks, one of the things that we are concerned about is the creation of these fracture networks. And when you do create these fracture networks, what you find is that you create fractures that connect. If you were to put a hypothetical producer here, so here's the well being fracked, and here's the hypothetical producer. If you were to put it at a certain distance, in this particular case, we are saying it's about 90 meters away above the injector. You find that there are fractures that are backbone fractures, which actually conduct fluid from one side to the other. And then there's dead end fractures, which are these gray fractures that are activated natural fractures, but they don't really contribute to the flow because they're isolated from all the other fractures. And then there is dead end fractures, which are essentially connected to the backbone, but do not flow fluid because they dead end into the matrix. So we distinguish between these types of fractures, and when we do a modeling of fracture propagation in naturally fractured reservoirs. And what we care about, of course, from a geothermal point of view, is what is the connectivity of the backbone fractures, and how planar is it, and how complex is the geometry of this? Because ultimately, that's what's going to flow fluid in it and create and extract energy from the system. So if you look at the backbone fractures, which are in red, versus the dead end fractures, which are actually very limited in this particular instance with this large stress contrast. And then you have isolated fractures that are sitting around the main connected fracture. So by and large, it's a reasonable approximation that we expect this fracture to be reasonably planar with some dead end fractures sitting around it. The natural fractures play a role, but don't play an absolutely dominant role in this geometry because of the stress contrast that we have. Now, if the stress contrast were reduced, the horizontal stress contrast were reduced, you would see a lot more of the dead end and isolated fractures being created, which are basically going to be out of plane fractures, which don't contribute to the flow. So that's an open question right now as to how confident are we about the sigma H max that we have in the model. We can also generate with the model induced microseismic events, and this is shown here. The one in the brown or the burnt orange, I guess, is colors are the simulated microseismic events. The rainbow colors are what is observed in the field. And I want to show you a couple of slides showing you what the connection or how well the simulation correlates with the field observations in terms of the microseismic events that are observed. The colors represent the moment, the magnitude of the microseismic events. So if you look at it in different two-dimensional slices in the XY plane, in the YZ plane, and the XZ plane, you find that you get some agreement, but clearly there is a lot of microseismic events occurring far away from the main hydraulic fracture being propagated, which we do not capture. That's no surprise because we really aren't modeling that far. We aren't really modeling that far. So, but some microseismic events that happen down here seem to be captured reasonably well, except for the events that are down here again, which again, some of these are sufficiently far away. We're not really modeling this volume. So we are concerned about what's happening close to the wellbore and directly above and below the wellbore. So we get nothing great, but we get something that looks reasonable. This actually shows you the time sequence of these events, and this is also revealing because here you see again the red is the field data, and you see these microseismic events occurring here far away much more quickly than we predict from the simulations. But then as these events multiply with time, you can start seeing simulation also predicting a large number of events occurring in the vicinity of these observed microseismic events. So there is some degree of correlation, although it's by no means great or perfect in terms of the microseismic events. Our goal was to try and see if we got close and then try to improve this over time as we go forward. We did try a couple of things. So for example, we don't really have an absolute or a good measure of the length of these natural fractures. So we said, what if we put longer natural fractures in here in the DFN? Would that change our microseismic a microseismic event map that we have? And so we did grow fractures in a DFN where the natural fractures were assumed to be longer, and you do tend to get more bifurcations to the main hydraulic fracture, still by and large planar, but you do tend to see much more turning of the fractures of the hydraulic fracture if you make the natural fracture distribution longer. Right, so here you see much more effect of natural fractures causing these fractures to be captured by the natural fracture and then turn along the natural fractures. And if you look at the microseismic events, you don't see as good a correlation between the events that you see in the field, the red ones, versus the black ones, which are the ones that are simulated. And so you don't quite see the same picture that we saw earlier. You see something that looks quite different, which leads us to believe that the base case that we had run seems to represent the microseismic events better than these longer natural fractures. We also tried to do this with shorter fractures. So in this case, we actually had natural fractures at 20 meters with an average, and then the base case was 40. And you can see that With shorter ones, the fracture tends to be much more planar, very little deviation from the primary orientation of the hydraulic fracture. The natural fractures are just too small to be able to capture and turn the hydraulic fracture very much at all. So we tried that, and then we saw what the microseismic event map looked like in the XY, YZ, and the XZ plane. And again, we don't see a good correlation between what we see in the field and what we see in the simulation. So again, points us away from this direction. The last thing that we have done is to actually locate the natural fractures exactly where the microseismic events were observed. Of course, when we do that, we are forcing the natural fracture network to conform to where the microseismic events occurred. And we can also specify the direction of these natural fractures in 3D and come up with what a DFN might look like in this scenario. We are actually in the process of simulating this and changing the orientation of the fractures so that we might be able to get a better agreement with the simulated natural fractures. What you end up, the other thing we're doing is we're actually running some simulations with a lower stress contrast. This is actually a 2D simulation, not a 3D simulation. But you can see that when you do have a lower stress contrast, you tend to get more branching. And you tend, so for example, you end up with dead end fractures like these. These are dead end fractures. You also get isolated, so these are dead end fractures here connected to the main fracture. These are isolated fractures, the gray ones, and these are the backbone fractures that traverse the entire distance between the injector and the producer and actually contribute to the fluid flow and the heat recovery. So you can see very clearly the impact of the stress contrast on the complexity of the fracture network that you create, and in particular the extent or the how well connected the two well bores are going to be. And of course, this is what we hope to get from the tracer simulations and other simulations that we plan to run in the future. So in what we plan to do in the future, in the coming month or two, is to continue to try to improve the agreement between the simulations and the measurements in the 3 frac stages that have been pumped in the 16A well. We want to conduct some simulations of multi-cluster frac simulations with the DFN that we have created, with a different number of clusters, different number of perforations per cluster, and different pumping schedules, so that we can ultimately recommend the best cluster design. What is the best design of perforation clusters and best frac design, so that we can get uniform fluid distribution, uniform proppant distribution into these clusters, and achieve a sufficiently large propped surface area, connected propped surface area, backbone fractures that would allow us to circulate fluid between the 2 wells most efficiently. Right? That is ultimately the goal of our frac scheme. So our next task will be to actually conduct these multi-cluster simulations with the DFN. And then using those maps of fractures that we create, simulate the heat and flow between the injector and the producer. The way we do that, and have done it in the past, so this is a reference that you can go to for the hydraulic fracturing test site we published. The fracture network that we create is simulated using a DDM, a displacement discontinuity approach. The reservoir mesh is unstructured, a mesh for simulating flow in or flow out of the wellbore, whether it's an injector or a producer. So we can look at the flow across the entire domain by looking at this unstructured mesh. We have also very recently come up with a faster method of doing this rather than this unstructured meshing, which is pretty cumbersome in 3D and time consuming, where we have a mesh-free integrated simulation of flow and heat flux which is a good approximation to the full finite element, finite volume type simulation that you would have to run otherwise. So these references provide you with some more details about this. We have done some thermal modeling of heat flux in these kinds of fractures. So we're actually finishing up a paper on looking at an efficient model for simulating fracture propagation and energy recovery in these naturally fractured reservoirs, and what is the impact of fracture geometry and topology and connectivity between these. And so you can look at the temperature distribution, you can look at how many megawatts of power is being generated based on the connectivity of these fractures. So we can do these sorts of simulations, and that's the plan for the Forge site once we have a good model for the fracture geometry that we're happy with, that we feel represents and agrees with most of the data that we've collected. So that is the plan. That's the plan going forward. There have been a number of publications that are relevant to this, and of course, all of this will be available to you on the Forge site, the data site. There's publications related to how we actually interact the hydraulic fractures with the natural fractures. This is the connectivity and flow in these fracture networks in naturally fractured geothermal formations. How different things affect how the fracture pressure, the impact of fracture growth affects the the fluid pressure in these uncemented natural fractures, and how that affects the creation of these natural fracture networks, and looking at some geothermal calculations, some temperature calculations, etc. So there is some papers that you might find interesting that we have been working on and publishing. So I think I've done my my presentation in exactly 30 minutes. So hopefully there'll be some time for questions. Thank you.
Thank you, Mukul. There actually are a few questions here. And I didn't want to interrupt. I didn't think it was worthwhile interrupting as you went, because I think we can kind of come into them right now. So Dharmetra, I know you asked and said you answered your own question, but I'm going to let you ask it anyway, just because I think that discussion might be beneficial to the group. Dharmendra.
Yes.
Yeah, go ahead. Please ask your question, because I think we'll be illustrative.
Yeah, actually,
Discussion.
from the first presentation of fracture propagation in the DFN, I was thinking that why the fracture is taking a rectangular shape from initially, because if you start the fracture, it should be kind of circular fracture, and then if you contain it, fully contained, then it might take PKN type of geometry. But
I'm sorry, you're not coming through very clearly. Is it just my thing, or is it everybody?
No, you're very muffled, like your microphone's in a box or a bag or something. So I'm having a hard time understanding you as well.
Yeah, I didn't understand that at all. So I'm sorry if you could.
Okay,
maybe...
I'm coming back. There's some problem with my
you still sound the same. I'm going to read the question you typed in.
Okay.
So the question was, it's curious that from the beginning of the fracture propagation, it takes almost a rectangular shape. He agrees that it can attain with a stress barrier, and later the shape propagation would take it like a PKN fracture. It actually leads to a kind of an observation or a question that I had, is that, essentially boundary effects on the results. If you're pressurizing up and hitting your top boundary, is that artificially changing the shape and some of the results, especially in regard to where we're seeing the microseismicity and essentially the direction of propagation? Did I do okay, Dharmetra? Is that kind of summarized?
Yes.
Oh, you sound perfect now too with the headset.
Yeah, there's some problem in my microphone. Sorry.
Okay, no worries.
Yeah. So certainly boundary effects can play a role. We do plan to increase the vertical extent of the model, and that'll give us an idea of what's happening. In the beginning, you do see more of a penny-shaped fracture. Of course, everything is rectangular because of the grid.
Yes.
But you certainly can see the effect of the boundary as the fracture approaches the boundary. But yes, so we should be increasing the height of the model to get us better estimates of what the height growth might look like. Yeah.
Okay, thank you.
Yeah, Colin.
Oh, hi, Mukul. Colin Sayers here.
Hey,
nice
Colin.
talk. Thanks for sharing that.
Sure.
I typed in my question during the first part of your talk, where you were showing the statistical fraction network, and I made the remark that it looks statistically homogeneous, whereas the microseismic was suggesting otherwise, and you've used the microseismic to try and adjust the network. My question really was, the way to do this properly, I think, is to use something like seismic tomography to image the variation of fracture density with location. And I'm wondering whether there's any plans for something like that in Forge, any plans to use seismic to look at the variability of fracture density with location.
Not to my knowledge, not to
Yeah,
my knowledge.
I'll take that question, Nicole, and I would say, Colin, I think I don't have, well, I'm not aware of any plans that are specifically addressed to like cross-hole seismic tomography between the wells. Although I would say that nothing is out of the question. So I know for the immediate near-term planning, I believe that is not in our schedules at all. And
yeah, I think for future, for future geothermal projects, when you're drilling a couple of wells like this, seismic tomography may be perfect because you can image the variation in fracture density with location, and that would choose, that would optimize where you put your stages.
True.
So
Yes.
I would recommend that, but I have no money to give you to do it.
I don't know if we do either. And if I go back to Joe Moore and ask for more testing, I think he'll hang me out the window here. But I will take that under consideration and pass that on to the project management team. Colin, thank you.
But Colin, it's a point that's well made, because the natural fractures do, of course, play an extremely important role. And what we're doing is doing it completely statistically and homogeneously around the whole volume, which certainly is not true. But there's no other way to do it at this point, except for doing it in a statistical way.
Yeah, and adjusting the fractures according to the microseismic events is nice, but of course it's a biased estimate in a way, because you're constraining it by those fractures that give a microseismic event. But for fluid flow, there may be different fractures in, so the fractures that give a microseismic event may be the fractures that are optimally oriented for slip. But fluid flow may, have a different pathways. So, seismic is a very good way of looking away from the wells.
I agree. I mean, I have no arguments. We're just doing the best we can with the data we have. So,
Thank you. I'm going to move on just for the sake of time. Wei Fu, would you like to repeat your question, please?
Yeah, sure. Thank you for the presentation, first of all. So I tapped in the question when you were showing the results with different natural fracture sizes. I just wonder how these natural fractures with different sizes handled, since basically the implemented range and power criterion is essentially 2D.
So the fracture sizes, what we're doing is we're varying the median size. There's a maximum and a minimum that shifts. So there is a statistical distribution of sizes, but the median is shifted to smaller or larger. And the distribution of these sizes, they're randomly placed in this volume with a given orientation, and the orientation distribution is specified. And of course, the volumetric density of these is also specified. They are placed in 3D. So
Thank you. Pingju.
Hi, Mukul. So yeah, just for my first question is size, because from the microseismicity, I think the height of the microseismic cloud is like 150, 160 meters. And I think your model is like 200 meters in total. I think that, as Rob and comment, there might be a boundary restriction to factor geometry. So yeah, another question is, so your current presentation is about stage 1, right? Yeah, I'm very curious about stage 2 and stage 3, because there's very difficult to match the operation history, I think, in the cluster in the perforation section. Have you done any preliminary analysis about that?
yes, yes, we have.
Yes.
Yeah, I don't have any slides for it, but we can certainly share some things with you on those too. Yeah. So
okay, yeah, I'm excited to see that. Yeah.
Okay,
thank you.
all right, yep.
Mark McClure, you had two questions there. You get the closing question before we transition to Ahmad. So, well, I'll make a
Okay.
few closing comments, but Mark, please.
Thanks. This is probably more of a comment, as is my typical style, but anyway, curious for your feedback, McCool. So first, I mean, I think 800 PSI is not a high horizontal stress anisotropy. I mean, when you look at stress maps, it almost always is higher than that at this depth. But another point I'd make is you're talking about the Renshaw-Pollard termination criterion as something that would create branching. But another thing is just what if there were just natural fractures that fluid leaks off into? So even if the hydraulic fracture just propagated right through a natural fracture, if it's big enough and conductive enough or capable of becoming conductive, you could have a lot of fluid leak off into that fracture anyway. At the EGS CoLab project in South Dakota, the hydraulic fractures they cut right through natural fractures because the natural fractures were cemented shut. But when they did see termination, it happened at one particular natural fracture. It was the one that was conductive. And they knew it was conductive because it was so big that they could see it in the mine shaft wall and they could see water seeping out of the fracture at the mine shaft wall. So that's another thing to consider is just if you initiate the simulation with some already conductive fractures and they're big enough and they're already percolating, you might get some complexity. But having said that, I'm not sure that we've identified such large faults at this site. So anyway, just some
No, it's
thoughts.
entirely possible that you can have very large faults. We don't have them in the model and we don't have any evidence of it at the site, but it's possible that you can have very large faults. Now, we have two papers on exactly what you said, which is when the fluid leaks off into the fracture and you have photoelastic effects and you have effects associated with pressure building up in these open natural fractures, you can modify the Renshaw-Pollard criteria, and we have done that. So that's something we have looked at quite carefully, and I'll send you a couple of papers on work we've done there.
Oh, cool. Yeah, thanks. I haven't seen them. Thanks. All right,
Mm.
appreciate it.
All right, thanks, Mark. Thanks, McCool. So I have just a few observations here as we close out before we transition over to Ahmad. What I find interesting is, your pressure match for this stage one or the open hole portion of the stimulation, McCool, you got a pretty good match of the pressure, but your interpretation of the fracture interaction being essentially a planar fracture or a single hydraulic fracture is somewhat different than what the Forge team did with a similar match to pressure, or maybe a little bit poorer. But so this is good because why it's good is we can test a whole bunch of different hypotheses here to try to get a better understanding of the site. It also helps call into or it calls out the need for detailed hydraulic testing of the two wells once so we do interwell flow tests. Particularly trying to push, we're trying to be able so we can have DTS and DAS fibers from healed or from essentially from wellhead to toe across both wells. We do some tests so we can see where flow exits and where flow enters between the two. So we can actually answer that question: is it a single fracture or is it a fracture network where this flow comes out? Because we can match the data, the seismic and the pressure data to multiple realizations of natural fracture system or the or a single fracture. So it'll be interesting to say. I'm going to have a few other comments, but I don't want to hold up Ahmad. So
let's Robert, let's discuss what you said, because we noticed that too. So let's get outside this meeting. Let's talk
Exactly.
about it and see
yeah,
what.
and I think some others may be interested in a follow-on detailed group. So
Yes, that'll be great. That'll be wonderful.
Great. Okay, and I think one person that'd be interested to be part of that group is our next speaker. Ahmad, would you like to take over and share your screen, sir?
Sure, thank you.
Thanks, McCool.
Can you, I guess, I'm assuming you can hear me.
Yes, we got you.
Okay, and then you can see the screen.
We see your screen.
All right, very well.
You're not in presenter mode. You're in edit mode, but we can
Well,
still
yeah, I
see
kind of do that so I know what's coming next, if you
it. Okay,
don't mind.
no, we don't mind.
Okay.
The floor is yours, sir.
So kind of, have an idea of, what to say next, the transition. So anyway, so there's not a whole lot of time, but what I'm going to do is
Ahmad, we have this venue for 45 more minutes.
Oh, okay, that's fine then. Yeah, but anyway, I don't think I need more than 20. So I'm going to just give you an overview of some of the work we have done on simulating the April 2022 multi-stage stimulation, and then looking at some of the questions revolving around the circulation potential that we obtain. And the contributors are listed here in alphabetic order. So what that means, I've done, the least amount of work, and my name is first because it starts with the G. But these are all folks who work in the group in different capacities, PhD students and postdocs. And the objective of our work is to support tasks in 2 Utah Forge R&D projects that I'm involved in. And the specific questions that we want to address is to forecast the rock mass response to injection and circulation, in particular, look at stimulated volume and its geometry, and also help assess the strain and the flow rates that we might observe in the production well. That's the second project that kind of needs that information, at least that forecast. And also there is a in situ stress determination study that we are undertaking. And so we're going to rely on MEQ investigations for that. So we would like to be able to identify the planes that have been activated, or the hydraulic fracture planes, and help better understand the in situ stress at the reservoir scale. So what I will present today is mostly on stage 3, although we have done a particular kind of category of simulations for all 3 stages. But the focus is going to be mostly stage 3, and the reason for that is because the seismicity data seems to be more conclusive in terms of at least what is going on in the reservoir than stage 1. So to build the model, we took the data from the native state built by the Utah Forge team, and added a few additional rock properties from our own work, and also guesstimated some other ones, in particular the stiffness, normal and shear stiffness of the fractures. And in building the model, we also found that we had to kind of move the perforation location for stage 3 from our previous idea of where it was, just to better match the microseismic data. So the DFN that we use, again, all of the DFN that you guys have put together, we looked at those, and we selected a volume of 300 by 300 by 300 meters around the perforation location, and then kept all the natural fractures within that volume. And then we ran the simulations. We realized we couldn't match the simulation time and the injected volume, so we added additional fractures to increase the leak off, essentially, and we had to add 13 more fractures of different sizes and different orientations to connect them to the DFN that was provided to allow for the volume essentially to reach reasonable levels, volume of fluid injected, and the simulation time. And what else on this? Yeah, and so when I say that we have a 300 by 300 by 300 meter volume, that does not mean that we have a boundary. There's no boundary here. This is just the scale of the DFN that we considered. Beyond that, essentially, the model assumes there's intact rock. And the reason we did that, obviously, is because the MEQ showed that, the maximum extent is about 300 meters from the wellbore, so there was no reason to include, a lot more fractures away from that boundary. So we tried to replicate the injection profile. We divided it into a number of steps, and we didn't consider the temperature-dependent viscosity. We just assumed water viscosity, and that for sure has some impact on the injection pressure and the width that we might get, at least in the short term. But nevertheless, the results are, as you will see, reasonable for considering the uncertainties that we have. For in one of the series of simulations, we consider the explicit interaction of the hydraulic fracture with natural fractures, and for crossing criterion, we use this particular version, Guan Wang, which improves upon Renshaw and Pollard's criteria and extends it to non-perpendicular intersections. And we have applied these simulations to the South Dakota, what was it called? Colab, man, I forgot already. The Colab experiment. And so with some interesting results and agreements, and the results have appeared in that paper that we have. So on the right, you will see the starting DFN that we have, and you can see the wellbore, going through it. This is just for stage 3, and then we inject into the perforation, which is simulated by a small circular fracture at the wellbore. And so this is the finished product. It's kind of noisy, but you can see there's a hydraulic fracture there. It's non-circular, it's not rectangular. Its geometry is kind of irregular. It's dictated by the restrictions that the surrounding natural fractures impose. There are some natural fractures that are taking fluid and they're opened, some sliding, and so they're dilating. So without you would expect that without any natural fractures, this should be the kind of geometry you get, more or less. And so it should not be circular, it should not be rectangular. This is essentially without any hindrance. This is not Utah Forge, but I just put it here just to give you an idea. And we have a movie of the dynamics of the hydraulic fracture propagation. Again, the actual hydraulic fracture is hidden. It's behind these fractures here, and we're injecting into it, and it's growing. And now you can see it. It's growing up, and it's trying to attain more or less the shape on the right side. But then, depending on the restrictions from the sides, it will change that. It will broaden a little bit to the sides, and it will come up and terminate against some of the top fractures there along its path. So again, this is we are assuming that the natural fractures themselves do not propagate in this process. That is, they do dilate, but we haven't allowed for any kind of wing crack formation or anything like that in this set of simulations. So in this image, you can see the resulting hydraulic fracture and dilated natural fractures superimposed on the field observed microseismicity. So we didn't simulate the MEQ. And again, it's not bad. You can see that there is a reasonable kind of level of agreement between where the hydraulic fracture is and which natural fractures have been reactivated and the cloud. Again, as I said before, previously we had a different location for these natural fractures in the perforation. We had to shift that by as much as I think 50 meters to get to this level of agreement. And so I don't know what that means really. It's just something that I'd like to share with you guys. And the pressure data that was observed is shown here, and the blue is our kind of attempt to match that. Yeah, it's it's a decent match considering again all the simplifications we have made in the fluid viscosity and etc. And let's see here. Yeah, so this is just shows you a side-to-side comparison. That's the hydraulic fracture there. That's the cloud there, and some of the activated natural fractures. So keep in mind here that some of these natural fractures were placed here in order to enable us to pump fluid. Otherwise, we had to stop, or the fracture would have to just keep going up. So this way, we were able to control the upward growth and lateral expansion a little bit, and while maintaining the injection rate. So now, what actually happened? We went back and looked at the microseismic data, and many of you have probably done this, and and seen the data presented, we compiled the data that was posted on the database, Utah Forest website. And so you can see right there, as we injected, there are some events here suggesting it seems that there was a hydraulic fracture right here that more or less is transverse to the wellbore, but then there appears to be some kind of upward growth there as you continue to pump. Let me speed that up a little bit. You can see it there. And then you continue pumping, goes up again a little bit. Okay, and I think you get to this one right there. You see that's reminiscent of maybe some kind of a wing formation. So this is likely a natural fracture, possibly, one would think. If this was the original hydraulic fracture, then this is probably a natural feature. And then this is probably, a natural feature or an extension of that, hard to say. And of course, when you stop and there's still events occurring, so there are some events appearing there, which could be, as the fluid, settles down and pressurizes the lower portion of the reservoir and cools it, possibly you get, additional fractures forming there. So we try to kind of taking a kind of a pointer from the Utah Forest team that presented a similar exercise last month. We tried to kind of come up with some ideas of what potential planes might have been formed, and this is just a rough estimate of the planes we kind of visually see. So there's something here, something there resembling a wing, maybe a major fracture there. That's a hydraulic fracture. There's something else there, and for sure there's something here which you can add. And then we're trying to improve this picture by, let me open this, see if you can see it. Can you see this? Yeah. Can you see this set of planes here that I just pulled up? So this is an attempt to find, kind of planes that best fit, these different clusters of microseismicity. And again, this doesn't really agree with what we have right now. So we're trying to find the best planes that fit the cloud. And so we have three or four other realizations. And so when we finalize that, our intention is to go ahead and redo this simulation with the new set of planes that we have. Now, there have been discussions in terms of, well, how do we know this is not noise? I mean, we have, of course, the lab situation is better controlled, but using lab data, we can see a clear correlation between acoustic emission and the fracture plane. And so, and here there's the density is high enough that would suggest that these are probably some planes or something's going on in those areas. So this was one kind of approach to simulating the stage 3. And again, we are working on stage 1. We didn't want to start with stage 1 because stage 1 is kind of has a lot more uncertainty associated with it. Here, at least we have this nice MEQ data that we can play around with. And then there is another approach that we took to simulating these hydraulic fractures, and that did not involve explicit modeling of fracture propagation. And I should have probably said this. This is a 3-dimensional displacement discontinuity method with poroelastic and all that, temperature, etc. So we model fracture mechanics there, but in a different approach that is based on just continuum modeling. We take a different approach that is we use a stress dependent permeability relationship to track the propagation of the hydraulic fracture in the continuum, essentially. And so we did that for all three stages, 1, 2, 3. And show you here the pressure profile for stage 3. And you can see here the kind of maroon, brownish maroon, if I zoom in, maybe here it might be better. The brownish maroon sort of zone is our hydraulic fracture, which is kind of elliptical somewhat. And then that's the actual microseismicity. So, you know, the agreement is not that great, but nevertheless, you know, it's good. But the pressure profile is not bad. The differences can be attributed to the fact that we didn't adjust for the friction losses. You know, that's about 6, 7, 8 MPa or so, based on our estimates. So we have done that for, you know, all three stages, stage 1, 2, and 3. And again, I will show you the stage 3, and then we have some results for stage 1, 2. But the purpose of this particular set of simulations was that to enable us to sort of assess the circulation potential. So this is a reservoir model, essentially. It's a reservoir model. And so we have added into it a pseudo kind of fracture propagation scheme that can help us replicate some of the hydraulic fractures. I mean, it would work really nice if we have a nice planar hydraulic fracture, it would, you know, it would work great. And so in order to do the circulation investigation, we had to estimate the resulting permeability. So we used Shapiro's approach. Essentially, he assumes that the microseismic front is essentially a function of the square root of 4 pi dt, d being the diffusivity of the rock mass. And so then we can use that to estimate the permeability. And so you can see a mean value of the permeability corresponding to the diffusion front evolving in time, and a maximum permeability. So we tend to take you know, the mean value in our simulations. In some simulations we have taken the max, but most of the times we just take the mean value. And we didn't apply this to stage 3 because the inherent assumption in this approach is that we have isotropic diffusivity, and for stage 3, clearly, you know, it's not really isotropic. You know, for sure we have a hydraulic fracture, and then there are differently oriented natural fractures too. So, you know, we have to come up with a solution which we're working on. And so, anyway, I showed you that already. We don't want to see that. And so we used different injection rates for the stage 2 and stage 3 cases. That is, you know, a post-stimulation. We want to see if we were to drill a production well there, and what kind of a, you know, connection we might have, and what kind of a circulation we can establish. The limitation we put on the injection rates is that the pressure, the resulting pressure, should not exceed SH min. So that's what we did. We built a, you know, much larger model here. So now this includes all the DFNs that were provided by the Utah Forge team, plus the hydraulic fractures that we simulated within this continuum code itself. And so we have a much higher permeability zone in the stimulated area. And then we subjected these to different injection rates. And so for stage 1, which actually turns out to be, first of all, it's larger, you know, so it's a larger stimulated volume, it appears. So it could take injection rates up to 50 kilograms per second. And so we can see here the forecasted injection pressures and the pressures of the production well. There is some sort of up and down here, and that's because we tend to inject for some time first before starting production. So the pressure tends to go up. And so one of the key issues in the success of EGS is this impedance. So and we should keep the impedance to about 0.1. And so you will see that currently the impedance value is kind of large. And so, so that suggests that the connection, perhaps based on our understanding, that is our simulations, the connection needs to be improved. Bearing in mind that, you know, we haven't accounted for some of the additional mechanisms that would contribute to permeability. So that, you know, we should include those, but we haven't. So this is a very conservative kind of, you know, estimate of the impedance. And so we repeated that for stage 3. And for stage 3, the maximum rate we could use was about 20 kilograms per second. So suggesting that, of course, the stage 3, its permeability is, seems to be, or its connectivity at least, and permeability structure in the zone between the injection and production well is such that we cannot inject at very high rates because of the increase of injection pressure above the SH min. So that was that, and then the last portion of the work that I kind of put together in a hurry this morning deals with the estimates of strain that we might get in the toe of the production well. So this is stage 1 DFN that we have, and we considered the fractures that intersect the wellbore only. And then we inject at, say, 1 liter per second. I believe this is from 1 liter per second into the open hole interval, and monitor the resulting strain here. In this case, we're computing that. And you can see here the time change of strain along the length of the fiber. So the point here was, can we get a detectable level of strain in the production well, and the results indicate that yes, we should expect that we can account for the or be able to record the strain in the production well. So this work is ongoing. This is just a very rough preliminary review. Obviously, the strain response is not the heart-shaped that you see in the petroleum sector, and that should be expected. This is a network, so its stress and strain signature will be different. So that's in a kind of a nutshell, where we are and what we've been doing. And so we have had a number of publications already at the GRC, and then we plan to report additional progress beyond what I've shown today at the Stanford workshop. And obviously we have ARMA and ERTIC and all that coming up. So hopefully we'll have some more findings by that time. Thanks a lot.
Thanks, Ahmad. I have some questions for you.
Yeah.
I'll refer to our audience first. So Colin, please ask your question.
Yeah, hi, nice talk. I enjoyed that. I had a question about fitting the planes. So in fitting the planes, do you limit the events to a specific time window? And if so, how does that relate to flow rate? Is there some information there?
So the planes that the realization that I pulled up in that HTML file, that does not recognize the time, but this one, this does. You can see this, right? So here we can actually identify the time at which a plane became very, very well defined. And so for example, this one here, it appears to come later after shut-in. So yeah, one could extract that information. We haven't focused on it yet. We are working on it, and so that's probably the work that we can report by the Stanford workshop.
There must be some relationship with flow rate there.
Yes, for sure. Yes.
Okay, thanks.
Mark.
Yeah, so it looks really cool, Ahmad. I was just wanted to ask about the Shapiro thing you were doing. I mean, hydraulic fracture propagation is not controlled by the diffusivity equation. So why match the data with the diffusivity model?
Right. And so we didn't do that for stage 3, right? So for stage 1, we feel that maybe for stage 1 that would be a good approach, but not for stage 3, and that's why we didn't do it for stage 3. Stage 2, I'm not sure. Again, we haven't really studied stage 2 in great detail yet. But yeah, no, I agree for sure. If stage 1 is in fact a hydraulic fracture, then yeah, we shouldn't use that. But I'm one of those who still kind of questions whether stage 1 was a hydraulic fracture or not. So we'll have to wait.
Well, that's fair enough. But I mean, even if that's like a quote shear stimulating natural fracture,
Mhm.
in that case, it becomes ambiguous what diffusivity you're talking about, right? Because it's not
Yeah,
like the
yeah,
conductivity is
yes.
constant over time and stuff. So
Sure, yeah,
Yeah.
that's a, that's an objection in general to Shapiro's work. But, it may provide, at least, some kind of an idea of, what we should use for permeability before we get to, before we have a well test that can tell us, right? So,
maybe, yeah. May I just point out the analytic solution for radial crack propagation is
Mhm.
time to the 4/9, which is quite close to 1/2.
yeah,
So, they could look very similar. Okay, well, thanks.
no, I
Appreciate
agree.
it.
Yeah, just a quick, if I could interrupt. Are you claiming you observed T to the half behavior?
Who, me?
Yeah.
No, I'm not, we're not claiming, any particular, behavior at this stage. And which particular stimulation stage are you referring to?
No, I'm
One-
just asking, did you try and determine the exponent?
No.
But cool.
Yeah, Ahmed, I just had a quick question. So, some of the figures you showed indicated that the natural fracture reactivations were at a finite angle to the vertical stress. And I was just wondering, do you think I think there was a subsequent figure to that, which I saw that had that. Do you think it's possible to have fractures that would open up at some angle to the vertical stress? Or is that, you think, unlikely?
Yeah, so if you look at, the values are still negative, so they're actually still closed. It's just that they dilated a little bit.
Okay. Yeah, towards the end of the presentation, I thought I saw something like that, but maybe you had a picture showing some of the fractures. There you go. Yeah.
Oh, this is stage 1, and so I don't know what we're showing here. So this is just a DFN. We haven't really we're not plotting the apertures here. So this is just showing the DFN, right?
Yeah.
And so,
Yeah. The only thing I wanted to mention was I think it's highly unlikely that you'll see anything that opens up at some angle to the vertical stress, in my view.
But they would dilate and then they would shear. So that's that's the thing. So I mean, if you look at the difference between SH-min and SH-max, then SV in this case is our max. So one of the horizontal ones is SH-min. So you do have shear, on these planes, which
you do have shear. That's for sure. Yeah.
And then if it slides, it dilates some, and so that's
okay. All right.
Yeah, and you see, in fact, that the strain changes sign, becomes positive. But anyway, yeah.
Great. Thank you.
Thank you.
Hi, Ahmad, can you show the slides of the pressure history match?
For stage 3, yes. This one?
Yes. So if you look at the pressure model, like from 15 minutes, it's kind of flat, but in the field test, it kind of decreasing. Could you explain like why is that difference? Like,
can you explain that a bit more so I can follow?
So in the blue line is the results, right?
Here.
Yeah. After 40 minutes, it's kind of flat. It's keep the same pressure, right?
Right. Yeah.
40 minutes.
It's coming down. So it's going up.
No.
It's coming down. Right.
After 40 minutes.
40.
After 40. Yeah. Here. Right. Okay.
Yeah. But the field test is decreasing, keep decreasing. Can you explain that?
Oh yeah, no, I can't explain. How could I explain that? I don't know. So this is just one. This is just one realization of a hydraulic fracture intersecting the natural fractures. Obviously, I would say that the field data suggests that you can't keep up pressure essentially. So you're losing fluid, your fracture is propagating, excessively here. So, we don't see the sign of really large growth. So I would during that time period. So I would suspect this is just natural fractures taking a lot of fluid, That's my, that's my
Okay.
assessment. But,
So
but I, yeah, we
it's,
can't capture that. We have to adjust stuff in the model to be able to capture that. So,
Yeah, so you think
and again, keep
because
in
the
mind
flow
that
is-
we didn't try to match, because, I don't believe in matching as such, because, when you don't even know what kind of a DFN you have, you can match the pressure somehow by playing around with things. But, what would that tell me? I don't really know.
Okay, yeah. So you think the pressure decreasing because the fluid loss to the natural fracture?
Probably.
Okay.
Yeah, probably. I mean, that's one idea. I mean, there might be other reasons, but
Okay,
that's
thank you.
we saw this. If I'm not recollecting wrong, I think this was observed in CoLab too. That the pressure would decline for some time. After we hit a natural fracture or two. Right? So.
Okay. Great,
But
thank you.
again, yeah, but it requires more analysis for sure. I don't know.
So with the approximately 10 minutes we have left, I do reserve the right to ask a question. And then I want to close it out. So Ahmad, you made some of those long-term flow models near the end. When you looked at the maximum potential flow rates, the impedance, that's the impedance there, or what I would call, specific yield, specific capacity, whatever you want to call it, is something that concerns me. It's something that's kind of essentially tells us how much horsepower we need to put on the injection well to make production. And so, with impedance numbers that are, around 1, we'll probably have to put more horsepower on a production well than we'll get out of the enthalpy of the fluid, right? So that's our worry, right? And so thank you for bringing this up. So my question to you is, in your models in these cases, you did say your reservoir permeabilities did have a stress or a pressure dependence. How much change were you observing at some of these higher injection pressures? How much change did you get in your estimated permeability fields?
Oh, I don't.
Several orders of magnitude, I would almost bet, right?
Yeah, we have. I have to go back and look, but I think it brings it in a way to the level of the stimulation time.
Okay.
Right.
Okay.
So
That's where I was going to get is,
yeah.
Without changing those things, even if you start with something as high as, an number goes like 10 to the minus 13 meters squared, you're not going to put 50 kilograms per second through some feature like that.
Yeah. No.
Raising it to 10 to the minus 11 or even maybe higher.
Correct. Yeah. No. Yeah. Yeah. And so again, this is just a what if kind of. And so, what we would do is that if we go and drill that well and attempt a circulation, and we can do 50 kilograms per second easily, then obviously our permeability is wrong, or stress dependent permeability needs to be corrected, and we can change it at that stage. But
now, another question, and I'd actually extend this to you as well, McCool, is when you're looking at this, the well right now, there's 2 perf completions in 1 open hole. If you're do you intend to do a simulation where you'll inject essentially into the well itself, where flow can be free to leave in whatever zone has the least impedance? Or what I'm saying is, will you be able to simulate a thief zone, or all the fluid go into the open hole toe if there's high perforation pressure drop?
Yeah, very good point. So I just want to point out that in these simulations, we isolated the zones. We did not inject in the open hole and let the flow evolve. We just said, okay, we're going to inject into zone 1 and 3. That's it.
Yeah. No. So in our simulations, the fluid will follow the path of least resistance essentially, and distribute itself according to the flow resistance offered by different sections of the wellbore.
Okay.
Yeah. So that that's not a problem. The only thing is that if you want to characterize the stimulated volume resulting from each of these zones, you have to inject into them in an isolated manner.
We may not be able to do that. Just so you know, from a logistical perspective, we may be trying to do hydraulic testing on the 3 zones that are there now, and then when like say McCool's team does their stimulation, their planning, we could characterize that zone, and then perhaps the Rice team, they do theirs, we can characterize those zones kind of together. I don't think we're going to have the resources to have a workover rig there and essentially to do straddle packers, what have you, to test each zone independently.
So even
It's
the
a hope, but it's maybe a hope and a prayer at this point,
And-
with the budget number we have.
but even the bridge plug stuff, it's not gonna be feasible? Because,
I
No?
don't think so. We'll see. Last question is, where is it here? Actually, no, last comment before we close it out is, I think what I'm really happy with both presentations today. And a lot of the questions I've been asking I'm probing, because we're doing some of the same work here to look at flow between zones, look at long-term preference, look at changes in either pore elasticity or thermal elasticity, and how that, the feedback for changes in permeability. And essentially where we try to place that, the 16B well. Now, what I'd like to have to do, and I think this will be a topic for maybe a sub meeting of the group, and I'll send a note out to the distribution, let's see who might be involved, is I want to start quantitatively comparing our model results for these type of simulations. So I want to make sure we have similar output formats, so we don't have to do a whole lot of back calculations, try to figure out and compare our results. So I like to come to an agreement, say whether it's, producing enthalpy, how do we parameterize, how do we put these production wells into our models? Are we just setting a bottom hole pressure and producing against some deliverability? Are we lowering the head? Are we simulating a pump? Whatever it might be. So we have some consistent basis for how we compare our results. I don't have the answer for that yet. These are just questions or food for thought. But if anyone would like to be part of that kind of a discussion, I'll actually, have a follow-on meeting that's separate from this series for anyone who's actually doing work and modeling of the site itself. And I'll open that up to all, but I would like to come to some agreement to make our work, quantitatively comparable. And I could see this could be essentially a review paper, probably sometime in probably late next year, that I'd like to publish this work to. So we could essentially, we're elucidating behavior of the models and of the system itself. So let's try to understand it best, so these learnings aren't lost, and I'll get them out into the open source literature. So.
I think that's a great idea, Rob. I think it's an important thing to do.
Okay, and we'll probably we can have a meeting to discuss this sometime middle of winter, either maybe coming out of Texas when it's nice and warm, after it gets pretty late here in late February, when things get the winters get long in Idaho, maybe we'll have to do a meeting someplace south, selfishly. Anyway, so I have no other comments from the group. Open mic, any closing comments, questions, snide remarks, anything you'd like to contribute? Well, thank you all. Thank you, Mukul. Thank you, Ahmad. Great presentations. You're doing great work. It's good to see all this progress happening. Stay tuned for next month. We may be talking about a couple of I'll communicate via our distribution channels about next month, and we'll go from there. Thanks all.
Thank you.
Bye now.
Bye.